Hi and good evening, everyone, and welcome to the introductory tutorial session for the device on wide bandgap device-based power electronic converter design. So this is the NPTEL course that is scheduled to run for 12 weeks, and over these 12 weeks, we will be reading a lot about um, WBG-based devices and their applications in building power converters. So before we go ahead, can you just give thumbs up as to whether my voice is audible? Hello.
Yes, it's audible.
Okay. Hello. Is my voice audible?
Yeah, sir. It is audible and clear.
Okay. Thanks a lot. Just hang on for a minute or two. I will try to change my audio device if possible, because some of you are having a problem, obviously. So, and then just we can start. So just hang on for 2 minutes. I'll just change my audio device. Yeah, so good evening once again. I hope my audio is much more clear right now. Is it fine?
Yes, sir, it's fine.
Okay, thanks a lot. So I'll just turn on my camera and I'll just share my screen. So kindly just hold on. Okay. Share this. So this being my first session as well, I'm having some trouble sharing my screen. So just hold on for a second and apologies for the delay, but I will try to share my screen. It's not allowing me to share the screen. So yeah, so I think now I can share my screen. Just a second. Share entire screen. Yeah, so is my screen visible? And are you able to see my slide?
Yes, sir.
Okay. Yes, sir. Yeah, so thanks. Good evening once again. I'm Nand Kishore and I'm pursuing my PhD from the Department of Electrical Engineering at IIT Delhi. So I am the TA or the teaching assistant for this course, that is Power Electronics with Wide Bandgap Devices. And of course, the course instructor is Professor Momita Das from IIT Mandi. So we will be covering this course over period of 12 weeks and we will be solving periodic problems as well. So camera, I don't know. It's not. Yeah, so I think now it's okay. So without much further ado, I'll just start over the course. So I presume you guys would have seen the lecture videos for week 1. So you had an introduction to WBG devices upfront, and then you read about device characterization, right? So you went through different types of device characterization, that is static characterization, junction capacitance characterization, and finally you touched upon a little bit of dynamic characterization. So as you would know, this is a tutorial session that's supposed to be kind of a problem solving session. So we will devote more time towards problem solving. And of course, this week was largely theoretical. So the problems would also be kind of MCQ or multiple choice based. But anyway, we will just see a very brief summary of whatever you studied and jump right ahead into the problems. Okay. Okay, so just an introduction to power electronics. Okay, so I'll just have my laser pointer on. Yeah, so the necessity for power electronics came about because of obvious the necessity for power conversion from AC to DC or DC to AC, vice versa, and of course from one frequency of AC to another frequency of AC. Okay, so an example is shown over here, and this diagram kind of encompasses all the applications of power electronics. So that is, let's say you have the 50 hertz grid, right? So you know that you have a transmission and a distribution system that takes up the power generated from a remote location, right? It may be some nuclear power plant or solar or wind or any kind of power plant, and it is supposed to transfer power from those remote areas to your consumer locations, right? Where most of the major cities are located, right? So if you have to do such a thing, right, the end user is going to be someone like maybe he might do a cell phone charging or he might do an EV charging, right? Or it might be to industries where there are a lot of induction motors running. So you understand that there is obviously a necessity for power to get converted from one form to another form, right? For instance, if you have to have some kind of device charging, right, that is phone or laptop charging, you need to have an AC to DC conversion stage over there, right? Similarly, nowadays we are talking a lot about AI, ChatGPT and stuff, but how does that run? What powers up those data servers or cloud storage applications, right? You need data centers for that, okay? And data centers are typically low voltage and high current applications, okay? So for that scenario, you first need to convert the 50 hertz AC into a DC. So this DC link voltage would be a different value, maybe 800 volts for a typical three-phase system. And then obviously, as I mentioned, you need to step it down from 800 volts to maybe a 48 volts or a 72 volts voltage level, okay? And correspondingly, the current would also be really high, right? So that's an application for data centers. So again, you see that there is an AC to DC conversion requirement and a subsequent DC-DC conversion requirement as well, right? Again, if you go for industrial or residential motor drives, right, where you need to have high horsepower induction motors, you again need to convert this 50 hertz AC into a DC, right? And then again, you have an inverter stage which may be running in scalar control or vector control. I think you might have studied about what is known as V by F control, right? That is, you vary the frequency and the voltage also varies, having a fixed flux, right? So again, you need to have power converters that will enable this conversion, right? That is, you have an inverter that will enable you to take up or power from a 400 volt DC link, and then you convert it into variable voltage and variable frequency output, right? And similarly, you have EV charging applications as well, right? So let's say you take a car battery, which may be typically around 400 volts, right? So if you have to have 400 volts DC, constant DC, first you need to convert the grid voltage, which may be around 230 volts, right? That is what you get at your houses. So 230 volt 50 hertz is converted into a DC, and then you charge up the car battery. Okay. Again, the charging can be wireless or wired, and you have a lot of categories in that as well, right? So these are just a few applications, and you have even more, right? You have UPS applications and so on. Okay. So in all of these areas, that is AC to DC converters or DC to AC or DC to DC, you see that as a system, it functions as an AC to DC converter. But if you go into the device component level, it is essentially a powered device, right? It may be a MOSFET or it may be an IGBT and so on. Okay. So the heart of these converters, AC to DC or DC to AC converters, is basically a MOSFET, right, or an IGBT. Okay, so based on how you modulate the devices, based on how you are going to switch the devices, you are able to get AC to DC conversion or vice versa, or even DC to DC conversion. So in this course, we will be dealing with what are the device level characteristic of those MOSFETs and IGBTs. So far, you have just studied that. So see, for example, let's say you take a buck converter, right? So let me change over to pen. Yeah. So let's say you take a buck converter, correct? So some guys, yeah, some of you may have studied something like this, correct? And you have an L filter, you have a C filter, and then you give it to the load, correct? So we always concentrate on how this inductor is going to satisfy the inductor volt second balance or the inductor flux balance, right? So what we tell is when S1 is on, right? So let me call this as S1 and this as D1. Okay. So when S1 is on, you tell that over here you are going to get V in. So VL would be something like this voltage minus this voltage, right? So VA and VB, right? So VL is going to be VA minus VB. I'm sorry. Yeah. So VL is going to be VA minus VB. So when S1 is on, VA is going to be Vin and VB is V0, correct? And when S1 is off, correct? You're going to tell VL is equal to what? VL is equal to directly minus V0. Okay. And then what you do, you apply what is known as the inductor flux balance principle, right? That is over one time period, the average inductor voltage is zero, correct? That is, inductor's flux is getting balanced, right? So let me take. So I'll just deviate a little bit just to make you guys understand the importance of these devices. But for that, let me add a new slide and start over again. Okay. So the buck converter that we were talking about, right? So you have a DC source. Let me draw it in some other way. Okay. Some of you may be familiar, some of you may not be familiar, but no worries, you will understand. Okay. So this configuration is known as a half bridge configuration. Okay. So this is Vin and this is S1. Let me call this as S2, right? So this configuration is known as half bridge configuration. Okay. So we will forget about the inductor and all, right? So what do you understand when S1 is on? Okay. So what do you understand when S1 is on? When S1 is on, this, let me call this as VA, right? So when S1 is on, VA is equal to V in, correct? And when S1 is off, VA is equal to 0. When S1 is off, and of course when S2 is on, VA is equal to 0. So let's say I turn on S1, turn off S1, right? So turn on, turn off of S1 continuously. So let's say the gate pulse of S1 varies something like this, correct? This is how my gate pulse of S1 varies. So my essentially my S this, right? Let me take a different color. Yeah. So yeah. So oh my. So the gate pulse of S1 varies something like this. So as S1 turns off and turns on, you understand that VA is going to be, when S1 is on, VA is going to be V in, right? And so VA is going to be V in, and when S1 is off, VA is going to be 0. Correct? So you are going to get a train of pulses that have discrete states, right? That is 0, V in, 0, V in, 0, and V in. Okay. So you are going to get a train of discrete states. So that is what I have got over here. Continuous. 0 V in, 0 V in. So this can be approximated like a square, right? It's a square wave. So over one switching cycle or switching cycle or one period, that is let me call this as 1 TS, right? That is one period of on off of S1, okay, from here to here, right? So over one period, you see that for a particular time you get V in, and for a particular time you get 0. So if you average it out, right? If you average it out, what would happen? If you average it out, you might get an average value something like this, and I'm calling this as V naught. Okay. So what would be the average value? You understand that the average of a square wave is going to be what? V in into whatever is this period. Let me call this as T1, and plus this, right? That is 0 into T2 divided by the total time, that is TS. Correct? So Vn into T1 over Ts. So we call this T1 over Ts as duty D, right? So that is why you get D into Vn. Okay. So this is what will happen if you average it out. Okay. And this is the relation which you are quite familiar with. This is in a buck converter, right? So how do we average it out, right? So how do we average it out? We can have some filter, some low pass filter, right? So you're having a train of square pulses and it is at a particular frequency, right? At a particular frequency corresponding to Fs, that is 1 by Ts. So if you are able to have a filter whose cutoff frequency is much lesser than this particular frequency, then you are going to get an output which would be a DC value, right? Which would be an average of this, correct? Basically, you need to have a low pass filter which would allow you to have something like this. Okay, so this is the idea, right? Yeah, so I don't know, I got logged out, but anyway, we'll just continue. So far, are you guys able to follow whatever I was talking about? Is there any doubt?
Yes, sir. Follow.
Yeah, I hope my screen is visible now. And I'll just continue from here. Okay. I forgot to turn on my camera. Yeah. Okay, so the idea is you need to have a low pass filter that can filter out the square wave and give you a fixed flat DC, right? And that's why to realize what is known as the buck converter, you add kind of a large L, right? And a large capacitor so that you maintain a fixed DC value and then you feed it to the load, correct? And across this you get a V naught, which is D times V. So this is the buck converter that we are all familiar about. But one thing, if you notice over here, we have assumed that these are very discrete states, right? That is, it is a flat zero and it is a flat V in, right? It's a flat zero and it's a flat V in and so on, correct? We never consider this transient area, right? This transition region. How does this happen? We never considered that, right? And makes sense also. So from whatever we have drawn so far, we understand that probably, so let's say I take one cycle, okay? So we understand that this length over here, this time interval is quite large. This time interval is quite large, but probably this happens in a very small time, right? So we are not concerned about it that much. It doesn't affect my converter operation in any manner, so I need not worry about it, right? So, and that's the reason probably we consider that S1 is on and S1 is off, correct? We never consider what happens during these transitions, right? So this is fine for a basic level, a UG level understanding of how a buck converter works, or for that matter, any converter, how it works. But this course is more about how do we design these devices? How do we choose these devices S1 and S2, right? And on what basis do we choose these devices? And in a converter design, does the selection of devices, does the selection of S1 and S2 affect my overall characteristic, my overall converter operation? How does the device selection translate to my converter's operating temperature, right? A converter may be able to operate at 70 degrees or 110 degrees. So how does my device selection relate to that, right? So these are questions that we will try to answer in this course. Okay, so this course, as you understand, is more towards the device level. That is, and that's how designers usually start. So this is kind of the starting point. Once you understand how the converter functions, right? So you know how the buck converter is going to function. Now, if you have to realize it in hardware, right? So the starting point is how to choose S1 and how to choose S2. Okay. So these are questions that we will try to answer, or that you will be answering in this course. Okay. Okay, fine. So Anyway, so this was just a small detour and we will come back to what we were talking about. Yeah, so okay, so now you understood that the device is going to be on off continuously. So you understand that when the device is on, right, it's going to carry some current, and when the device is going to be off, it's going to block some voltage. Okay, so for instance, let me take another slide. So are you guys understanding till this point? Any doubts?
No, sir.
Okay, fine. So we were okay. So we were just telling that a device is going to be on off, something like this. Okay, and you would know that I'm not going to go deep into it, but you will know that in a buck converter, right? In a buck converter, how would the inductor current look like when the device is on? The inductor current is going to be something like this, and when the device is off, you are going to get an inductor current something like this in steady state, of course, right? You understand that the converter is operating in steady state, so something like this, right? So this is the charging interval and this is the discharging interval, correct? Okay, and this slope is basically Vn minus V naught over L di by dt, right? So this is Vn minus V naught by L, and this is Y naught minus V naught over L. This is for a buck converter. Okay, and this is your inductor current. And if you guys have studied about what is the current of S1 and S2, right? So you will know that during this interval S1 is on and during this interval S2 is on, or rather the inductor would be freewheeling through the diode, correct? So this is the operation of a buck converter, or over here as well, right? The inductor current would be freewheeling something like this. Okay. And when it has to deliver power, when S1 is on, you will know that the current is going to be something like this. Correct? I think you are quite familiar with the operation of buck converter. Anyway, so you understand that S1 and S2 are going to be on alternately. Okay. So what would be the device current of S1? Let's say. So the device current of S1 or IS1 would be something like, it would be equal to the inductor current, right? It would be equal to the inductor current when S1 is on. When S1 is off, obviously it will be 0. So the device current is going to look something like this. This is not according to scale, so pardon me for that, but you understand that it's going to be something like this. It's going to be a train of something like this. This is how your S1 is going to be, right? Okay, and you will be having an average value called capital IL, and you will be having an average value over here as well, right? Let me call this capital IS1. But anyway, we never think of what is happening during this period when the device is actually turning on, and what is happening during this period when the device is turning off. Okay, so what's happening during this period? We never think about it. So this is what you will be answering in this course, right? So you understand that I hope you guys have studied about control systems. That is, let's say you have a second order system, right? So second order system can be a simple RLC network, correct? So you understand that for a step input, the response that you might get can be something like
Sir, your screen is not.
screen is not visible.
Yes.
Yes, sir. Not
Oh,
visible.
sorry, okay, just a second. From how much time it was not visible?
For about a minute only, sir.
Just now, na? Okay. Yeah, so I was talking about this, like, were you guys there when I drew the inductor current? Was my screen visible?
Yes, yes, yes.
Yeah, okay. So I was talking about a second order 100 amp response over here. That is, if you give a step change in the input, what you can expect is something like this. This of course signifies an 100 amp response. or you may even get something like this, right? It can be overdamped as well. So something similar you can expect in your circuit as well, in your device behavior as well. So you understand that when the device was turning on, right? That is, initially it was off over here and suddenly it turned on. You suddenly gave the gate source voltage for the device, right? So there is a step input, right? You are asking the device to change from on state to off state and off state to on state, right? In a step change manner. So you can expect something like an underdamped response, probably, or even overdamped. It depends on your design, but you can expect something like this. So the objective of this course is to study what is actually happening over here, right? So what's actually happening over here? What dictates this overshoot? Okay. What can be the overshoot? How can we minimize it? Right. So these are some things that we will try to answer. Right. Okay. So I was telling that during turn on, you may see something like this and something like this. Make sense? Okay. So this is about the device current. Okay. And if you think about the device voltage, right? What would be the voltage blocking of the device? So when the device is on, what would be the voltage across the device? When the device is on, the device is generally on in the ohmic region. So the voltage drop across the device, VDS, when the device is on would be I into RDS, whatever is the drain source resistance of the device or the drain source resistance of the channel. So this would be a very small number, right? RDS is in the order of a few milliohms, and let's say you send a few amperes of current. So maximum you will get a device drop. Yeah. So maximum you will get a device drop of the order of a few volts, just a few volts, not more than that. Okay. Do you understand? When the device is on, the drain source voltage across the device or the voltage across this device, right? VDS as I call it, between this point to this terminal, right? When the device is on, it would be I into RDS on. Okay. So there would be a very small voltage over here, just above zero. Okay. And when the device is off, right? That is when this device turns off and this is on, then what would happen? The voltage across this device would be almost zero, right? So the entire Vin voltage is going to appear across S1, right? That is the device S1 is going to block the entire DC bus voltage or whatever is your supply voltage, Vin. So Vin, let's say Vin is around 400 volts or something like that. It may be any number, depends on your application once again. But you understand that when it was on, it was blocking a few volts, and when it was off, it will be blocking 400 volts or something like that, right? And it is something like this. You understand, right? It will be blocking 400, then voltage is zero, then blocking 400, then it falls, and so on. Do you understand? This is VDS1. Okay, when the device is off, it would be blocking some voltage, right? So let's say this is 400 volts Vin and this is 0. So 0 Vin. Not exactly 0. Let's say this is IDS into RDS, right? When device is on. So this is IDS into RDS, I into RDS. And this is Vin. So you see that it's going to block a huge voltage. Then suddenly it is falling down to almost zero, right? So what happens during these intervals, right? So this is what we will be studying in this course. So you can again understand that there would be some underdamped response. So we'll be seeing something like this, and okay. And this is very, very critical, whatever is this overshoot. Okay. So are you guys able to follow? Now the point is, there would be an overshoot in VDS, right? Let's say you use a device which is, let me take some number, for example. So let's say your Vin is around 400 volts, right? Your Vin is 400 volts. and the device is rated for 650 volts, right? So Vn is 400 volts and the device rating, right? So the device rating is 650 volts. That is, the device can block 650 volts, not more than that. Okay, and your Vin is 400 volts. Now, as I was mentioning, you might have an overshoot in VDS. I'm sorry. How do we raise this? Yeah. Oh, I don't know why yellow is not going, but anyway. Anyway, yeah. So let me redraw it once again. Yeah. So if you see what is VDS, right? So it's going, yeah. So it's going to be I into RDS, then block some voltage. Just a second. So it's going to block some voltage, then it's going to be on, block some voltage, and so on. So and as I was mentioning, there is going to be an overshoot over here. Okay, something like this. So what is the magnitude of this overshoot? And let's say you are going for 400 volts VIN and the device is rated for 650 volts. Sometimes if you don't design it properly, this overshoot can go beyond 650 volts and the device can be damaged. Okay, device can be in danger, and it has happened to a lot of people as well if there is improper design. Okay, so we will be studying what dictates this overshoot. How do we model it? Okay, so these are things that we will be trying to answer in this course. So is this fine so far? Just from a device perspective, I have told you. So we started off with a buck converter, right? And then we just saw how the device current and the device voltage are going to look like. And we understood that there will be some overshoot. There might be some overshoot. And if the overshoot is large enough, it can lead to problems, right? It can lead to damage of the device. Okay. So is this fine? Is this enough motivation as to why to study this course? Okay.
Yes,
So
yes.
yeah, thanks. So this is one part of it. Okay. Fine. So and the other part is let me take. Yeah. So again, I will go back to the device current and device voltage waveforms. So let me draw IDS and VDS in the same graph now, right? So IDS is something like this, correct? Okay, and your VDS is going to be something like, so the VDS will be blocking. So let's say this is VDS and yeah. Okay, so it will be blocking voltage when the device is off. So it will be during this interval. Okay, so this is your VDS. So this is your VDS and this is your IDS. Now the point is, what we again consider during the normal converter operation is that it is in discrete states. That is it is on or either it is off. There is no transition that we consider, right? So what happens during these transitions, right? So for some period of time, so let's say you zoom in over here, right? If you zoom in over here, you will see that um, first the device current will increase something like this, right? So this is the zoomed in part. So the device current will increase something like this until it reaches the steady state value. Okay, device current will increase, and The device voltage will not fall until your current has increased to the total value. You will study why later on, but you understand that the device current, the device voltage will be like this. So VDS is like this, and only after the device current has increased to the rated value, your device voltage will fall. Okay, this is the zoomed in region. So you understand that for some time, right? For some time, what do we understand? There is a definite time taken for the device current to rise. So this is your IDS, right? This is your IDS. There is a definite period of time taken for the device current to increase. Okay. And there is a definite period of time taken for the device voltage to fall down. Okay. So the device was blocking 400 volts previously, and let's say the device current is 30 amperes, some random numbers, right? So initially device current was 0, it increased to 30 amperes, and VDS was 400 volts. It will fall down to what? It will fall down to I into RDS, right? So point is during turn on, you understand that it will take some time. It will take some time, known as the turn on time of the device, T on. It will take some time for the device current to increase, and it will take some time for the device voltage to fall. You will study how this happens in this course. Okay. Why is the device current increasing like this in a particular fashion? I have drawn this linearly for simplicity, but if you go into the device modeling, you will understand it's not linear. But anyway, for now it's fine. So you understand that there is going to be some time for the device current to increase and some time for the device voltage to fall. And another characteristic is the device voltage will not fall to 0 until your current has increased.
Sir, your voice not audible.
Yeah. Once again, so yeah. So this is what is known as the turn on time of the device, right? So we will try to model how this happens and why this is important. So now you understand that if there is an overlap, right? So there is obviously there is an overlap between the device current and the drain source voltage of the device for some time, right? So if there is an overlap, what is the implication, right? So you know that for any device, any generic for any generic application, if there is an overlap of voltage and current, right, there is going to be some loss, right? So because you know that P is simply V into I, correct? So if there is an overlap, if P is also, if V is non-zero and I is non-zero, then there will be some overlap and there will be some losses. So this is what is known as the turn on loss of the device or the switching losses of the device. Okay. So because the device is turning on, during turn on, there is going to be some overlap between the device current and the device voltage. Okay. And this is going to cause losses. And if your overlap time is higher, if the voltage and current are going to be overlapping for a longer period of time, it is going to be larger, right? The power loss is going to be even larger. Okay. So this is something that we will try to characterize in this course. That is, how much is the power loss? Okay. If this turn on time is higher, you understand that there will be more time of overlap between the voltage and current, therefore more losses, right? And similarly, you can do a similar exercise for during turn off as well. That is when your drain source voltage or your current would be falling from a particular value to 0, and then your drain source voltage would be increasing, right? So you will see that your drain source voltage is something like this. I'm not going into the details of how this happens and all, but again you understand that there will be a T off. Okay. So again, it's going to cause some losses, right? That is something that we don't want. We will try to understand how this happens, right? So this is about the switching losses. So in order to find out your switching losses, and mind you, this can be a huge component, right? You might think that it may be very small, but it's a huge component and it's a huge cause of heating up of the device. Okay. So this turn on and turn off time, this may be of the order of a few nanoseconds or tens of nanoseconds or hundreds of nanoseconds or even microsecond. Okay. We will try to understand for what devices it is, how much, and how do we estimate what is the turn on and turn off time and all. Okay. Right. So yeah. So I will just go into a bit of electric vehicles and where these devices are getting used. Okay. And I think this picture is kind of self-explanatory, but it's a very good demonstration of how much power electronics is being employed nowadays. So let's start from here. You have the AC grid, right? Then what you need to do first, you convert AC into a DC. Only then you can charge the battery, right? Because battery is obviously, you cannot charge a battery with directly feeding 230 volts 50 hertz, right? Battery obviously needs a DC voltage to get charged up, right? So you have what is known as a PFC stage, as a power factor correction stage. Okay, you will convert AC into DC. So can anyone tell how do you convert AC to DC? Rectifiers. So the simplest rectifier that we all would have studied about is what is known as the diode bridge rectifier, correct? That is, you have DBR, that is a diode bridge over here, right? So, correct? And then you have a large filter capacitor and then you just feed it to the output, right? So if you have a large capacitor, then what you get is you get an output that is almost DC, something like this, correct? But one of the drawbacks is if you have a large capacitor over here, the current that is drawn from the grid, right? The current that is drawn would be peaky. Okay, I'm not going into the operation of DBR, but you will study that it is something like this. And what you require is what is ideal is something like if you have a sinusoidal current. Okay. So you don't want a peaky current, you need a sinusoidal current. Okay. In order to get a sinusoidal current, you have what is called as a power factor correction stage, right? So this is a kind of a power electronic converter that can convert AC into a stiff DC voltage while maintaining a sinusoidal input current. Okay, you will study about these more in master's level courses, but just to give you a flavor, this is called a PFC stage. And again, in these PFC stages, you generally have WBG devices. Okay, I'm not going to go into the topology and all because this course is obviously not on that, but you understand that it will convert AC into DC while maintaining a sinusoidal input current instead of having a peaky current, something like this, right? Because a capacitor draws a peaky current, it will not draw sinusoidal input current, obviously. Okay, right. So either you convert AC into DC, or you can have a solar system, solar PV inverter that will convert DC into another voltage DC, right? So either way you get a DC bus over here. Then what do? You convert DC into high frequency AC. Okay, so you have a DC voltage and you will convert it into a very high frequency AC. High frequency AC means something like of the order of few kilohertz or hundreds of kilohertz or even megahertz. Okay, few kilohertz or megahertz level high frequency AC. Okay, right? So you can do something like this high frequency AC, and then what do? You can connect it over here onto your car charging terminal, right? That will kind of convert your you connect it over here, that will convert your high frequency AC back to DC, and that will convert high frequency AC back to DC. And this is what is known as an OBC, on-board charger for electric vehicles. This is the heart, or this you can tell is the core of an electric vehicle. That is, you plug in your whatever is your voltage over here, or it can even be grid voltage, right? This terminal can even be a grid voltage. Okay, so grid voltage you connect over here, then what would happen? The grid voltage would get converted into a DC voltage, correct? Again, it happens through a power converter. It's called an OBC, onboard charger, and this onboard charger will charge up your car battery. That is one way. Or if you don't want to go wired, if you want to go wireless, right? That's what companies like Tesla are researching on, or you might have heard of something called electricity. Okay, anyway, so what they do is they will have one coil on the roadside and another coil on the car, right? So as the car moves, the magnetic field of this coil will link with the other coil, the secondary coil, right? So due to that, due to Faraday's law of electromagnetic induction, there will be a voltage induced across this coil, and that voltage is converted into DC once again, and you charge up the high voltage battery. Okay, and from the high voltage battery you can run the motor of the car. Okay, from the battery you again convert this battery DC into an AC voltage, and you do V by F control and you run the car motor. You understand, right? So there is a lot of power conversion involved over here. Okay, first there is an onboard charger to convert whatever you supply from the outside. You just plug in some voltage, right? So there is an onboard charger to charge up the car battery, and from the car battery, it is the car battery. From the car battery, there is a power electronic converter to convert the DC into an AC voltage and run the car motor. Lot of power conversion involved. So in all of these power converters, you will be using these devices, and the industry is slowly gravitating towards WBG devices. Okay, fine. So these are just some slides that I took from the lecture courses, just to give, just to start it off. So you have the metal, semiconductor and insulator, and obviously the difference between them is the band gap, right?
So for metal, there is no band gap as such, and there is an overlap between the valency band and the conduction band. So the metal is directly ready to take up the current, right? And in semiconductor, there will obviously be some band gap which you will be bridging if you give appropriate excitation in terms of gate source voltage. If the gate source voltage is more than threshold voltage, then the band gap is bridged, or else the band gap remains, right? And or else the depletion region forms and the band gap remains. And in case of an insulator, there is going to be a huge band gap, and even if you try to bridge it, there is going to be a dielectric breakdown, right? Okay. And coming into power semiconductor devices, for power electronics, you have devices based on silicon, right? You have devices based on silicon carbide, and gallium nitride. Okay. And they come in different packages. So these are known as packages. Okay. So for instance, this package is called a TO247 package, right? And it will have separate leads called drain, right? Drain, then gate, source, and Kelvin source, right? So this is one package and this is another package. Okay. So they come in different packages. This package over here is called an SMD mounted package, and these are all through hole packages. So SMD means surface mounted. That is, you understand that there is nothing, there is no terminal that will go into the PCB. They are just like, you will just solder it onto the PCB. Okay. So for instance, if the PCB is something like this, right? Right. So how do you place these devices is you will be having the GAN devices just on the PCB. Okay. Just on the PCB directly. Whereas these kind of devices will go into the PCB. That is, let's say you imagine in 3D, then you will be having 3 holes on the PCB or 4 holes on the PCB. So all these 4 terminals will go into the PCB. Okay. They will protrude from the backside of the PCB as well. Okay. So these are known as through hole devices, and this is a surface mounted device. And you might wonder why these are important, but you will understand that these leads over here, right? These leads over here are very crucial for device switching. As I was mentioning over here, you might see something like this, right? So this time over here, or even you might see something like this. Okay. This overshoot and all, and this time, these are all functions of these small parameters like these leads. Okay. These leads can make a huge difference in terms of the turn on and turn off times. Okay. Because you see this as one lead, right? But this one lead can be represented as something like an inductor and a resistor. This inductor can be a few nanohenries and this can be a few micro ohms. But you will see that this nanohenry of inductance causes a huge impact, right? Why? Because this time is also of the order of a few nanoseconds. Okay. Because of that, the nanohenry of inductance is also considerable, right? So in order to avoid this, people have gone for this kind of direct mounted packaging. So no leads, directly you just solder it onto the PCB. They are called surface mounted devices. Anyway, so this is about the packaging, and one characteristic feature of gallium nitride devices is due to the device physics, right? I'm not going to the device physics, but due to the device physics, there is no anti-parallel diode in GaN. Okay, no anti-parallel diode. Inherently in the device structure itself, for a silicon or silicon carbide MOSFET, you will see an anti-parallel diode, right? But for a GaN device, there is no anti-parallel diode. Okay, this is due to device physics. Right. So about the double pulse test, I'm not going into it right now, but just one more thing before we jump into the problems is, let me insert a new slide. Just a second. Yeah. So I presume in the lecture slides as well, you would have studied that even though you represent a device, something like this, right? Correct? So you would have studied that due to the device packaging, right, and the die structure, you will be having parasitic capacitances between the drain to source, between the gate to source, and between gate to drain. CGD, right? CGS and CDS. So these are the device capacitances, or they're also called junction capacitances. Okay. So why are these capacitances formed, right? So what happens inside a semiconductor device, right? When you turn it on, there is going to be a channel that gets formed, right? And when you turn the device off, or when you remove the gate pulses, then there is going to be a depletion region, right? So what is a depletion region? So let me just jot it down over here. Yeah. So what's a depletion region? So depletion region means there is going to be an absence of charge carriers, right? So there is going to be an absence of charge carriers. Okay. So if there is a gap between charge carriers, so you have N region on one side, let's say, and you have P region on one side, and in middle there is no charge carriers, right? So it means that there is no free path for recombination of the charge carrier. So in that case, obviously there will be a built-in potential between the P region and the N region, right? So you can approximate that as a capacitance, right? Because you can imagine that P is one plate of a capacitance and the N region is one plate of a capacitance, and in the middle there is a depletion region or a dielectric. Okay, and that is how the capacitance gets formed. And you can understand that if the voltage blocking increases, let's say you're at 100 volts and let's say you're at 400 volts, right? So then it means that obviously the depletion region's width is going to vary. And as the width varies, you understand that the capacitance is also going to vary. Okay. So these capacitances are intrinsic to the device. They are not some capacitance that someone has added. Okay. They are due to the device switching, right? As the device turns on and turns off, as the device blocking voltage varies, the capacitances are also going to vary because these capacitances are formed. Okay, because obviously there is a n doped region and a p doped region, and there is a voltage blocking between that. Then it means that a capacitance is going to form, obviously, right? So these are the junction capacitances of a device. So basically you have the gate to source capacitance, so you have gate, drain, and then source. Okay, so even though you have these three capacitances, generally, while we represent them, we call them as CISS, or the input side capacitance, COSS, or the output side capacitance, and the reverse transfer capacitance, or the CRSS. So how do we find that out? Okay, so we will go back to first year Thevenin's theorem, or yeah, so that will help. So let's say you want to find out CISS, right? So let's say I want to find out what is CISS. Okay, that is the input side capacitance. Input capacitance. Correct. So what do you do? In order to find, so you forget about the capacitance. You if you want to find out the input impedance of any network, right? You want to find out the input impedance of any network. How do you find that? You will short the voltage source on output side and open the current source. Correct. So over here, the input side is where you give the controlling voltage, that is the gate source voltage, right? So input side is gate. Input is basically gate to source, VGS. And what is the output? As a consequence of you giving VGS, there is a drain to source current. Correct? So this is the relation between in a MOSFET, right? A MOSFET is a voltage controlled current source, right? MOSFET is what? MOSFET, any generic MOSFET is basically voltage controlled current source. That is, the controlling voltage is VGS. You give some voltage, there is going to be a current, a drain source current, right? That is why you would have heard the relation as well. I channel is what? Some GM times VGS minus VTH. Right? Correct? You might have studied this in analog as well. That is, based on the gate source voltage, the channel current or the drain source current is going to vary. So MOSFET is a voltage controlled current source. So the input side is gate source and output side is the drain to source. Okay. So if you have to find out the input capacitance, right? Input side capacitance, what will you do? You will short the output side. Okay. So let me take another slide. So what you do is you have something like this, and yeah. So you had something like this, a capacitance over here, and a capacitance over here, and a capacitance over here, right? And now I want to find out, looking from here, I want to find out what is CISS. So if I have to do this, what will I do? First, I will short the output side. So the output side is drain to source. I will short the drain to source, shorted. So you forget about this capacitance. Okay. So seeing from this, since these two terminals are shorted, drain and source are shorted, right? Drain and source are shorted. So what is the effective capacitance looking from input side? That is, looking from the input side, CISS, right? So looking from the input side, CISS, you can tell that CGS, right? So this is CGS and this is CGD. So looking from this, think from gate to source, okay? So looking from this, since drain to source is shorted, you can tell CISS is CISS is basically CGS plus CGD, correct? Correct. So are you guys able to understand this? How CISS is equal to CGS plus CGD? Just short the output side. If you short the output side, what happens? Drain and source are now shorted. So effectively, what is the capacitance? CGD is going to come in parallel with CGS, right? That is, CGD is in parallel with CGS. Okay. Because drain and source are shorted. Okay. Now let's do the other exercise. I want to find out the output side capacitance, correct? So we'll draw something like this. Then I will take this capacitance, and this capacitance, right? Now I want to find out what is the output side capacitance, COSS. If I have to find out the output side capacitance, what will I do first? I will short the input side. As I was telling, input is gate to source, output is drain to source. So output side is drain to source capacitance or COSS, right? If I have to find out what is COSS, I will short the input side. I will short gate and source. Okay. So I will short gate to source. If I short gate to source, what happens? Gate and source are now the same points. So COSS will be basically, this is CGD, this is CDS, right? So gate and source are shorted now, right? So if you see from here, you understand that CDS is in parallel with CGD. So COSS is basically CDS plus CGD, because CDS and CGD are in parallel, because we have shorted the input side, short the input side. Okay. Similarly, if you have to find out the input capacitance, short the output side. Effectively, both the remaining capacitances come in parallel, right? So this is COSS, correct? And CRSS, or the reverse transfer capacitance, is basically this linking path, that is CGD, between drain and gate. Okay, so any doubt over here? How did we determine CSS, COSS, and CRSS? I'll just pause here for a minute. Can you tell if this is fine? How we did CISS, COSS, and CRSS? Is this fine then? Can we move ahead?
Yes, sir.
It's fine, sir. Yes.
Okay. Okay, so now that we have studied a bit about devices, right? So we studied about the capacitances and how to obtain that, right? And we also studied about the different packages of MOSFETs, right? And we studied some applications of power electronics, and mostly we built up some motivation as to why we are doing this course. Okay, so this should provide you enough motivation as to why we are doing this course, right? So with that as a motivation, we will jump into problems right away. Okay, and as I was telling, the mostly the problems are theoretical, so we will not be taking much time to cover all of that, right? So I'll just pause here for 2 minutes. I'll just fill up my water and come, and then we will resume from problems. Okay, so just hang on for 3-4 minutes. I'll just fill up my water bottle and come. Yeah, thanks for hanging around, and we'll just resume with the problems. Okay. So most of the problems are quite simple. So we'll just go through them one by one slowly. And if you have any doubts, you can just pause me and ask. Okay. Okay. So which wideband gap devices are known for their high breakdown voltage and thermal conductivity? Silicon carbide devices, gallium nitride devices, Si devices, or gallium arsenide devices. So the answer is silicon carbide devices, right? And the reason lies in the fact that the electron volt of silicon carbide devices is much higher than the rest three. Okay. Therefore, and also if you see the thermal conductivity is typically expressed in watt per meter Kelvin. Okay. So thermal conductivity is expressed in watt per meter Kelvin, right? Or even watt per meter into degree Celsius. So that is, it indicates how much the device is able to dissipate heat. Okay. So if you are going to use for high power applications, there will be more and more heat. If the device is able to dissipate more and more heat, then it means that the device is suitable for high power applications. And obviously silicon carbide scores over there. That is, it has a high thermal conductivity, which means that it is much easier to remove heat from the device die. Okay, silicon carbide die. And if you see the high breakdown voltage as well, so that is why you see that silicon carbide devices are nowadays available in the range of more than 650 volts. Okay, 650 volts and 1.2 kV is a very popular number. Okay, most of the silicon carbide devices that you see, right, they are rated for 1200 volts, 1.2 kV and 900 volts. Even there are devices with 1.7 kV, right, 1.7 kV, and research is going on for 3.3 kV. Okay, so silicon carbide enables you to do that. You can't get these high voltages with GaN and all. So with GaN, you have devices only till 650 volts. Okay, so with GaN, you have devices only till 650 volts, right? And the reason is GaN doesn't have a high breakdown voltage. SiC has a very high breakdown voltage. Okay, and what it allows you is that what it implicates is that most of the DC bus voltages, right? So DC link voltages, you may call it, or DC bus voltages. So they are mostly either 400 volts or 800 volts. Okay. Car battery, if you take, right, it may be somewhere from 200 to 400 volts, or for high power applications, it may be till 800 volts for probably electric trucks, electric buses, or even high-end cars, right? So it may be 800 volts. So this is a conventionally used battery rating, that is 400 volts or 800 volts. So if your Vin is going to be 400 volts or Vin is going to be 800 volts, the devices need to be rated for much higher. Correct? And this is where SiC devices come into play. So you can use these 1.2 kV devices for 800 volts battery applications, right? That is why a lot of chargers, right? Lot of chargers use SiC devices. The reason being that if you have 800 volts battery at the input or output, you need devices that can block 800 volts. And a device which has a rating of 1.2 kV is a safe selection to block 800 volts. Whereas you understand that gallium nitride devices are rated only for 650 volts, which means that you can use it only for 400 volts battery applications. And typically, if you study conventionally used systems, 400 volts is used as DC link for single phase systems, and 800 volts is used as DC link for three phase systems, right? So again, it gives you the flexibility that SiC devices can be used for both single phase as well as three phase systems, whereas GaN can be used only for single phase systems. Make sense, right? So yeah, so the question was not about, so these are just some extra stuff that it's good to know, but idea is for high breakdown voltage and thermal conductivity, go for silicon carbide. Okay. Right. So, which characteristic makes wideband-gap semiconductors particularly suitable for high-frequency application? Is it low breakdown voltages, slower switching speeds, high thermal resistance, and faster carrier mobility? So, lower breakdown voltages, obviously not. Just now I was mentioning that silicon carbide can block voltages more than 650 volts easily, right? And for less than 650 volts, you have GaN. Correct. So it's not at all a problem. Blocking voltage is not at all a problem. Okay. And slower switching speeds, definitely not. So I can tell you that SIC has a turn on time. We were studying about the turn on and turn off times just some time back, right? That is this time over here. This is the turn on time, right? During turn on, what happens, and during turn off, what happens. So this turn on time for SIC, the turn on time can be as slow as less than 100 nanoseconds or 200 nanoseconds. So 100 into 10 power minus 9, right? So that's the time we are talking about. And if you see for gallium nitride based devices, right? For devices based on gallium nitride, GaN as we call it, the turn on and turn off times can be less than 10 nanoseconds. Okay. And I'm currently working with gallium nitride devices. I have seen devices that turn on in 5 nanoseconds or so. Okay, really fast. So it's not a switching, it's not switching speeds because they can turn on and turn off very, very fast. SiC devices and gallium nitride devices. By the way, so I hope you guys understand that when we tell WBG devices, right, wide bandgap devices, we mean devices mostly based on silicon carbide and gallium nitride. Okay. Yeah. So lowest breakdown voltage is not the answer. Slowest switching speed is not the answer, and higher thermal resistance. So thermal resistance, just for your information, is denoted by a symbol called R theta. Okay, R theta, and it is expressed. It's called thermal resistance, right? So it is expressed in degree per watt, degree Celsius per watt. That is, for 1 watt of power dissipated, what is the temperature rise? Okay, you understand that for 1 watt of degree dissipated, it will tell you what is the temperature rise. Okay, so can anyone tell, is it better to have higher thermal resistance or lower thermal resistance, and why? So for 1 watt of power dissipated, what is the temperature increase? That is the degree per watt. So can you tell whether it is beneficial to have higher temperature resistance, higher R theta, or lower R theta? Anyone?
Lower R theta is better.
Correct. So lower R theta is better. I'm sorry. Lower R theta is better. The reason being that for the same power loss, right, the temperature rise would be lesser. Okay. So it means that you can push towards higher power. If you push towards higher power, obviously there will be more power loss. But the advantage you get is the temperature rise would be lesser. Okay. So obviously, wide bandgap semiconductors, as I was telling previously as well, right? They have a high thermal conductivity. High thermal conductivity, which means that R theta is lesser, right? So R theta is lesser. Okay, R theta is lesser for WBG devices compared to silicon, right? So obviously, and all the WBG devices have very high carrier mobility. We would have studied it in class 12 as well, right? About mobility of electrons. So the mobility of electrons or mobility of charge carriers in WBG devices is really high. And that is what actually enables switching times of the order of 100 nanoseconds, 10 nanoseconds, or even less than 10 nanoseconds. Why? Why are we able to get such high switching times with such very fast switching speed? The reason is because the carrier mobility is really high. Okay, that is why you get these very fast switching speeds. Okay. Okay. So what
Sir.
aspect of thermal management poses a challenge in the design of converters with wide bandgap devices? So lower power dissipation compared to traditional devices, right? So lower participation compared to traditional devices, difficulty in dissipating heat due to smaller die sizes, limited availability of heat sink materials. So definitely not. You have a lot of heat sinks available in the market. Okay, reduce sensitivity to temperature variations, no. And lower power dissipation compared to traditional devices, no. We will take for the same power dissipation where the heat temperature rises lesser, right? So the challenge is actually in dissipating the heat due to smaller die sizes. So if you see the die size, right, that is the size of the device itself. Okay. So for instance, in the starting, we just saw some photos of SiC and gallium nitride, right? Yeah. So if you compare this size and this size, in photo you may not be able to judge it. But over here, if you see the size of this, it may be, this may be 5 mm. Okay, this is the size and this is 3 mm. This is the size of gallium nitride. Okay, very, very small. And if you take this as well, it may be somewhere around, this may be around, let's say 4 to 5 mm. And this can be somewhere around 7 mm. Okay, very, very small devices. Whereas you take IGBTs, which come in module packages, they are very large, right? Even silicon devices. So the idea is, if you open this package, right? So this is a package, as I was mentioning earlier, this is a package. If you open this, inside this, there will be a die. Okay, that is the actual silicon carbide. Okay, this is the actual silicon carbide. Rest of it is just packaging, taking the terminals out. Okay, so just for information, I will draw how it looks like. Okay, so what you are seeing outside is just this black box, right? You are just seeing a black tab. I'm drawing this. Okay, this is, you're just seeing this outside, but inside it, if you open it inside, right, there will be a silicon carbide die, and the die size would be quite small. So this is the silicon carbide die. Okay, and in this die, you will have multiple connections. So let's say this will be the gate and drain, source, and so on. So you will be connecting this to the outside terminal. So you have terminals over here, correct? That is, these are the terminals that I will draw. Okay, these are the terminals. I have drawn it outside. Okay, so inside the package, if you break open the package, what you will actually see is there will be very, very thin wires connecting like this. Okay, so this is the actual die. That is, the red colored part is the actual die. And this is just the package. Okay, now the point is, for SiC and gallium nitride, the size of this die is very, very small. Okay, the size of this die is very, very small. This is the actual SiC. Rest of it is just packaging. Okay, so the size of the die is very, very small. So as we were mentioning earlier, all the power losses are going to happen inside the channel, right? On the channel, that is on the die, inside the die. So in a very, very small area, there is going to be a huge power loss, right? And the entire temperature rise that we are talking about, right? All the temperature rise is going to happen in a very, very small area. Okay, and that is the challenge, right? So you have a huge temperature rise that's happening in a very small area. So how do you take out that heat, right? That is the challenge. You understand, right? That is, in a very small area, there is a huge delta T increase, that is a temperature increase, and taking out that heat is going to be the challenge, right? On the contrary, you understand the other thing, that is, you have a large area and in that the heat dissipation is happening. Because the area is already large, the heat kind of spreads out. So there is better thermal dissipation, right? But if the device is smaller, then the same amount of heat has to get dissipated from a very small area. So that is going to be the challenge for us. And that is what this question means. Okay. That is, what is a significant challenge in designing converters? That is, Yeah. So what aspect of thermal management poses a challenge? That is difficulty in dissipating the heat due to smaller die sizes. Okay. Next. So what is the significant challenge in designing converters with wideband gap devices? High fabrication cost compared to traditional silicon based devices? No. Most of the nowadays, if you see, most of the SiC devices are also at the same cost of silicon devices, right? Limited availability of wideband gap materials? No. Reduced thermal conductivity leading to higher operating temperatures? No. In fact, we just studied that the R theta of uh, WBG devices is lesser because they have better thermal conductivity, right? So WBG devices have better thermal conductivity. Okay, R theta is lesser. Okay, and the thermal conductivity is better. And increase electromagnetic interference due to faster switching speeds. Yeah. So this is the answer. So why does it cause EMI issues? You will study more about it as you progress, probably in week 6 or week 7, if I remember correct. But you understand that I will go back to this diagram over here. Yeah. So in a very small interval, there is a rapid current rise, right? That is in a very small time, there is going to be a current rise. So this is basically what? This is di by dt. The di by dt will be very high. Okay, there is a huge current rise in a very small time. Right? The di dt is very high. So what can happen is there can be some parasitic inductance L. You will study about parasitic inductance, but there can be some parasitic inductance L and there will be some induced voltage, right? L, there can be some LDI by dt. Okay. And because of this, what can happen is there can be some voltage fluctuations, very fast voltage fluctuations, and these are what are known as EMIs, electromagnetic induced radiations. Okay. So this is something that you don't want. Okay. And this is happening why? Because of fast switching speeds, you have high di by dt, high dv by dt, and that will cause these issues. Okay. You will study more about EMI issues later on. Okay. A dash connection in packaging can greatly improve the switching performance of SiC MOSFETs. So it is Kelvin source. So I'll go back to the diagram. Yeah. So if you see over here, right, you just know about three terminals, right? Drain, source, and then gate. Gate, source, and drain. Gate, source, and drain. But you observe over here, there is drain, D, and then there are two sources, S2 and S3, and then gain is, the gate is in terminal 4. Okay. So this particular terminal, that is 3, is called the Kelvin source. Okay. So the source terminal which is nearer to the gate, that is called Kelvin source. Okay. And the advantage you get with the Kelvin source is that, see, the idea is between the gate to source, you want the distance to be as small as possible. Okay. Between the gate and between the source, you will want the distance to be as small as possible. Why? Because if the distance is larger, right? If the distance, let's say the gate was over here instead of here, then what you will be having is some kind of a physical connection to this point, right? You will be having a physical connection, right? If the gate terminal instead of this was this, you will be having a physical connection, right? Physical connection can be through PCB, or you can have a wire or something like that, or a terminal, something like this, or some kind of connection, some kind of aluminum connection or whatever. So then what can happen is because of that physical connection, you will be having some parasitic resistance, that is an unwanted resistance, very small, and a parasitic inductance. Okay. So these inductances can cause problems if you are doing high switching, fast switching. Okay. So these inductances can be the cause of overshoots over here. Okay. So you don't want that. So in order to minimize this, so you see over here, the gate is over here, right? And the source is over here. So there is a significant distance between this gate and this source, correct? So in order to minimize this, what manufacturers give is what is known as a Kelvin source. So Kelvin source is that, okay, you connect your gate source over here as well. So let me erase it off. Yeah. So what manufacturers give is anyway. So over here you understand that you give VGS between the gate and source, and the drain source conduction path is also like this. Correct? So the source is kind of the terminal point for you to give the gate source voltage and also for the drain source current to pass on. Okay. So what device manufacturers give is, okay, they will take a separate tapping from the source terminal till this is Kelvin source. And there will be another terminal which is the power source. Both of them are internally shorted, but the idea is physically this source is closer to the gate. This source is closer to the gate. Okay. So the inductance is lesser, path inductance is lesser. Do you understand? Do you follow what is Kelvin source? The source terminal which is closer to the gate, right? So that the path length is much lesser, right? That is called Kelvin source. And this is the power source. The drain source current will flow something like this, correct? I mean, it will flow something like this through the die and then it will go like this. Do you understand what is Kelvin source? Anyone?
Sir,
Who
can
does
you please just another time?
repeat? Yeah.
Uh,
Okay, sure.
uh,
So the point is, you forget about Kelvin source and all, right? So let's say, okay. So let me draw a MOSFET. Correct. So this is the gate and this is the source. Okay. So what you are applying is basically a VGS over here, right? You mentioned you consider two cases. This is one, right? And on the other instance, I will draw another MOSFET. And let's say you give the gate source voltage like this. Physically, this is lengthier. This part is lengthier. Okay. So this is case one. This is case two. So which one would you prefer?
first one.
Why?
The distance is shorter.
The distance is shorter. So why the distance need to be short, right? So we will try to answer this. Okay. So let's say, um, so have you seen an inductor? So you will, so to wind an inductor, what will you do? You will take a core, right? And then you will be having something like this. Correct? This is an inductor, right? Hmm. So you can imagine of a solenoid as well or something. You take a core and you wind some wire. This is an inductance. Okay, and this inductance can be somewhere around a few microhenries or a few millihenries. Okay. Now the point is, if you go to smaller and smaller distances, right? That is, if you actually analyze a wire, let's say I just take a wire. Imagine this is a wire. Okay. Hmm. Intrinsically, we imagine that a wire is a direct short. It's a direct electrical connection between point A and point B. This is what we assume, right, for a wire. Okay. But if you see, right, if you see, the wire will be intrinsically having some resistance. Okay. It is just copper wire, but still it will have some resistance. Okay. And it will have some inductance. Okay. What is this inductance? This inductance is coming about due to the physical dimensions of the wire. Okay. And you can understand that as the wire length increases, both of these R and L are also going to increase as the distance increases. So this inductance, you may not, this is not some microhenry or millihenry of inductance which will affect your circuit operation. This is very, very small. This is some nano henries of inductance, right? And this is some micro ohms or even lesser. Okay, so micro ohms and nano henries of inductance. So even if you add or subtract nano henries of inductance to your actual inductance of few micro henries or millihenries, it's not going to cause any trouble, right? So the point is, if you analyze any wire, right? So there is something called as an RLC meter that will tell what is the R, L, and C of anything that you connect across it. So if you analyze a wire, the wire will have a particular value of R, particular value of L, and a particular value of C. Okay, and you will see that the wire, as the length of the wire increases, the L also increases, the inductance increases. Okay, and this is true not only for a wire. Let's say you take any connection, any physical connection, as the distance increases, there will be some inductance that will increase. Okay, that is why I'm telling, physically, if the source is shifted from here to here, right? So intrinsically, if you analyze a device, so I will just go into the device model a little bit. So if intrinsically, if you see inside a device, the gate terminal that you see is the outside gate, right? There will be some inductance like this, some resistance, right? Like this.
Sir, your voice is not clear.
My voice is not clear.
Yes, no.
Now is it fine? I just turned on and
Yeah.
turned off. So intrinsically, if you see, right, there will be something LD, some LS, okay? So some LS and some LG, okay? So there will be some gate inductance, some drain inductance, and some source inductance, okay? These are called parasitic inductances. Parasitic inductances as in like you don't want them to come. They are like parasites. Like you didn't design those inductances, they are inherently coming. Just a while ago we were talking about device capacitances, right? Device capacitances, they are not some capacitances that you went and added into the device. They came because of the presence of depletion region, because of the device itself, because of the separation of the charge carriers. There will be some capacitances formed. Actually, this is separation. So because of the separation of charge carriers, there is some capacitance that is formed. Like that, because of a physical connection, there is some parasitic inductance, few nanohenries of parasitic inductance. Okay. So that is why I'm telling. Now, if you have, now you take two cases. One is with this, and the other is there is a lengthier source, which means that this over here, the LS is going to be larger. So LS2, the second case, LS2 is going to be more than LS1. Okay. So if your inductance is larger, then the inductance is going to affect the dynamics of your how the gate source voltage will change, right? Earlier we told that if you have a step change, you will see something like this, correct? And you can understand these dynamics are affected by RLC networks only, right? So you don't want them to, so you want the LS, LD and LG to be as minimal as possible, as slow as possible. They are parasites. You don't want them ideally. So that is why what manufacturers give is, so we will go back to the figure once again. So you see over here, just so you see over here, there are two options. One is, so the
Hello.
gate is over here fixed. Hello?
Hello. Yeah, my
Yeah.
one doubt is that is this Kelvin source and power source both are isolated?
No, they are physically connected. Of course, they are connected.
Means if we use any gate driver, generally we have to use some bootstrap circuit for upper FET
Correct.
in a half bridge configuration. So if we
Correct.
use this Kelvin source package, can we get rid of this bootstrap connection or still we have to use?
Of course, we need to use. See, Kelvin source, if you see physically, it is shorted. Just that some inductance is not getting included. That's it. But it's a physical short. It's a connection only. So for all practical purposes, you I mean, for normal on state, and if you consider S is on and S is off, S is on, S is off, switch is on and off, you just consider both the Kelvin source and power source are same. Okay, just that during the transient, I'm talking about this particular region. Only over in this region, Kelvin source comes into play, or else like during the steady state, you know that under steady state, an inductor behaves as a short, right? During steady state, a capacitor is open and an inductor is short. So it doesn't matter during steady state whether your source is this or this. Okay, both of them are shorted only. Fine. Only during the transient we are talking about. So during transient, if you are able to avoid some inductance in the loop, then the dynamics may be better. That is why we try to have this Kelvin source. That is, physically you can see that this Kelvin source is much near to the gate compared to this source, right? So yeah, so this answers, right?
But if we see like when you are giving the PWM pulses or any gate pulses to the FET, that time if both are separated, then with respect to Kelvin source only, we have to provide the gate pulse, right, to the FET.
Correct, correct.
And we can give the high voltage or any our power source to respect to our this source power source line, correct? So in that case, both these two source externally you have to short it, means divert.
No, that is why
secondary
I'm
side.
telling. They are internally shorted. They are internally shorted.
Okay.
Yes, they are internally shorted. Because if you take a multimeter, just take some random device, take a multimeter, and you just check the continuity of terminal 2 and terminal 3, it will show you a short. Okay, they are internally shorted. No worries.
Okay.
Okay. Just from the purpose of gate driving, in terms of gate to source voltage, where you give your gate source voltage, it is preferable to give it in the Kelvin source, because the Kelvin source is physically near to the gate. So the inductance, loop inductance is lesser. Okay. 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 So the next question is it fine? Does this answer the Kelvin source problem? Do you understand what is Kelvin source now? Hello, am I
Yes, sir.
audible? Okay. So what is the impact of high electric field breakdown in WBG devices on the device size? It increases the device size, it reduces the device size, it has no impact on the device size, it requires additional cooling mechanisms. Okay. So this is something related to the device properties. So I'm not going to dwell on this too much, but point is, what happens is if there is electric field breakdown, right? If there is electric field breakdown, then the width of the region decreases, width of the depletion region decreases. So effectively the device size is going to reduce. Okay. Right. So far any doubts? These are mostly just theoretical questions, which I think you will be able to answer these questions quite fluently at the end of this course. Okay. But anyway, we'll just move ahead and go to the next set of problems. That is, you read about pulse IV testing, and you read that pulse IV testing is done to characterize the output characteristic, that is VDS, IDS characteristic or the output characteristic. You read about your VGS, IDS characteristic or the transfer characteristic. These are things that you typically find in any data sheet, right? And you also read about VGS and IGS's gate source current, leakage current characteristic, and you also read about VDS and IDS or the drain source leakage characteristic. Okay, and all of these characteristics are typically carried out using pulsed IV test. That is, you don't continuously keep the device on, you just turn on and off the device once, that's it. Within that time you try to capture everything. So these are pulse tests. So the reason we do pulse tests is, the idea is, okay, so if you keep the device running for a long time, then the device is going to heat up, right? And it may lead to variation in its values, and it may even lead to failure of the device. Okay, because pulse IV tests enable you to even go to extreme values of voltages and currents, right? Because it's for a very short time, so the temperature doesn't increase that much, right? You always know that the thermal time constant is low, right? You heat up something, it takes some time to heat up, right? So that is why even if you, let's say the device is rated for 100 amperes, let's say, right? And you go to 150 amperes for a very short time, nothing will happen to the device, right? Because you just turned on the device for 150 amperes, right? And you kept the device turned on, let's say for just around 10 microseconds, right? Just for 10 microseconds, you gave 150 amperes and you turned off the device, right? The device will not fail, okay? Because it's for a very short time and the temperature will not increase that much, okay? So this is the advantage of pulse IV testing. That is, it allows you to go beyond your rated condition, okay? So I think I answered it over here. That is, the purpose of pulse IV testing is you can go to extreme values without temperature increase, without significant temperature increase. That is, you are not, basically the device doesn't recognize that you have gone to that much high values, right? Because before the temperature can increase to so high values, you have turned off the device. Generally, the thermal time constant is of the order of few hundreds of microseconds, or milliseconds. Okay, so this is the thermal time constant. Okay, so which means that, so what is thermal time constant for this much increase in temperature? How much time does it take? Okay, so now the point is, if you are subjecting the device to very high values just for a few microseconds, right? So before the device temperature increases too much, right, you are turning off the device again. So it's kind of a safe operating scenario for the device, right? So pulse IV testing allows you to control the operating temperature conditions without significant temperature increase. Okay. Right. So I think we have covered nearly 10 problems in today's session, right? And this is almost 8 o'clock. So, okay. So I'll just, can I cover still 3-4 more problems and then we can stop, or should we cover this in the next week? So what do you guys suggest?
Continue, sir.
Okay, can I continue? I will just take around 5 minutes. We will just see through this set of problems, and then the next set of problems we can go on for the next week. Okay. Okay. So which parameter is critical in determining the steady state behavior of a power device? Gate source voltage, ambient temperature, packaging type, test fixture design, and on-state resistance. Okay. So you understand that once you give the gate source voltage, right? Once you give the gate, let's say you give a gate source voltage of 15 volts, right? Once you give 15 volts, the device is on, right? Because when VGS is more than V threshold, device is on, right? So in steady state operation, the gate source voltage doesn't have any bearing, right, on the behavior of the power device. If gate source voltage is higher than threshold voltage, device is on, that's it. You will understand how the gate source voltage increases and all, that's for later. But in steady state, in transient, gate source voltage plays a role, but in steady state, gate source voltage doesn't play a role, right? Okay. And we are talking about steady state. And ambient temperature, yes, as we were talking earlier, the thermal time constant of a device is very slow. So ambient temperature plays a role in determining the steady state behavior. So as the temperature varies, you will see that. So let's say this is your RDS, right? And this is your temperature. So as your temperature increases, your RDS also increases. That is, the drain source channel resistance also increases. So as your temperature increases, your drain source resistance increases, right? So this is a parameter Packaging type doesn't matter, right? Text fixture design again doesn't matter, and of course RDS on, right? So both of these are kind of interrelated, and of course they impact the steady state behavior. So one parameter that's not taken over here is gate source voltage. So for a particular value of gate source voltage, it doesn't matter, right? But point is, okay, so I will just conclude over here, but I want to discuss something that is an implication of the gate source voltage. Okay, so I will go back to a device characteristic. So let's open a data sheet, right? And let's try to understand. I hope my screen is still visible.
Yes, sir. Smart.
Okay. So we will go to a device data sheet, right? And so this is a device from our room, okay? Yeah. So are you guys able to see the data sheet? It's a 650 volts rated 21 ampere device.
Yes, sir.
See, and some packages do not come with Kelvin source. See, this has only 1, 2, 3. It doesn't have the Kelvin source. Some packages come with Kelvin source. So it totally depends on the manufacturer and the device package. Okay. So anyway, our interest is see over here, the drain source resistance, right? RDS on. RDS on is mentioned as typical 120 milliohms at 25 degrees, right? At 25 degrees, 120 milliohms. And at 150 degrees, it increases to 172 milliohms, right? As temperature increases, RDS increases. And also see, it is at a particular value of gate source voltage at 18 volts. If it is, let's say 15 volts, the RDS will be different. Okay, so gate source voltage has a bearing, even though they have not taken that up in the options given, right? So if we go back to the question, yeah. So in this, they haven't considered gate source voltage as a parameter for the steady state behavior. But point is, gate source voltage, if you see minutely, it has a bearing. See, at 18 volts, it is mentioned at 120 milliohms. Okay. If you go to the device characteristics, just go to the device on state character. Yeah. No, just hold on a second. Yeah, electrical character. Yeah. So you is this curve visible? Figure 4, typical output characteristics. So
Yes,
in
sir.
this, yeah. So in this, you see for different gate source voltages they have plotted 8 volts, 10 volts, 12 volts, 14 volts, 16, 18, 20, and so on. So you see what is the X and Y axis, drain current and drain source voltage, right? So at 18 volts, right, there is a particular slope at 18 volts, correct? Unfortunately, I'm not able to annotate on this. Anyway, so correct. So at 18 volts, there's a particular slope, right? At 14 volts, there is a particular slope. At 12 volts, there is a particular slope. What does the slope indicate? Slope is basically ID by VDS, which is 1 by RDS, right? 1 by the drain source resistance. So what do you observe? As you go to higher and higher gate source voltages at 18 volts, right? At 20 volts and all, the slope is much higher. Okay, slope is much higher. So if the slope is higher, RDS is what? RDS is lesser or higher?
Lesser.
RDS is lesser. So as the slope is higher, RDS is lesser. So what you are seeing at higher and higher gate source voltages, the RDS is going to be lesser. So instead of operating the device at 12 volts, it is better to operate at 18 volts, because at 18 volts, the slope is higher, RDS is lesser, so lesser conduction loss. Okay, do you get it? Everyone? Just from the output characteristics, I'm telling you, take two curves. So I will just draw over here if you want. We'll insert a new slide. Okay, and I will have two curves. So one is this, right? And let's say this is VGS at I'm sorry, VGS is equal to, let's say, 18 volts, and there will be another curve, VGS equal to 12 volt. You focus on the ohmic part, that is the linear part, right? And you see the slope. So this is the slope of the curve at 18 volts, and this is the slope of the curve at 12 volts, right? And what is the slope? So this is ID in amperes, and this is VDS in volts, right? So basically, your slope is what? Delta ID divided by delta VDS, correct? This is your slope. So what is, this is I by V, right? Basically 1 by R, 1 by RDS. So if your slope is more, RDS is lesser. What do you see from the output characteristic? At 18 volts VGS, slope is higher, correct? So RDS is lesser. At 12 volts, slope is lesser, and therefore RDS will be higher. Do you understand? This is why we always want to operate the device at higher gate source voltage. See, the device may turn on at threshold voltage itself. At threshold voltage itself, the device has turned on. But why are we not operating at threshold voltage? Threshold voltage may be somewhere around, let's say, 6 volts or something. Let's say 5 volts, or even somewhere around that, 4 to 6 volts. Okay, threshold voltage is somewhere over here. We can operate at 4 to 6 volts also. Why we are not operating? Because as you go to higher and higher gate source voltage, the slope is higher. Therefore, the RDS is lesser. So conduction loss would be lesser. Okay. Does everyone
But
follow?
if we, excuse me, hello. But
Yeah.
if we use higher VGS anyway, we are means increasing the current, means anyway we are burning the device, and more for the more current for same drain to source voltage. For the higher gate to source voltage, our drain current will be more. So in that part
Right.
anyway, we are reducing the conduction load, but still we are burning the
No.
device.
Wait. So let me clarify this. See, the device operates in 3 regions, right? What are those regions? One is ohmic region, one is cutoff region, and one is saturation region for a MOSFET. What are the regions of operation? So yeah, so before I continue to this question, this is the I think till this question, this is enough for this week's tutorial session. So thanks everyone for attending. I'll just continue answering this question, but if anyone has any work further on or something, they can leave. So this concludes today's tutorial session. We will not be seeing any more questions, but I'll try to answer this question. Okay. Yeah. So see, a device operates in 3 regions: ohmic, saturation, and then cutoff. Correct. So in these 3 regions, you can approximate the device into 3 equivalent models, correct? So this is your device. Okay. So when it is in ohmic region, correct? So when it is in ohmic region, it is like a resistor. RDS on. Okay. When it is in cutoff region, it is like a switch which is blocking some voltage. Okay. And when it is in saturation region, do you know how the switch is approximated? The switch is approximated as a voltage controlled current source or a dependent current source. Okay. So again, going back to the conventions, if you draw something like this is an independent current source. If you draw something like this, it's a dependent current source. Anyway. Okay. So this is a voltage controlled current source, VCCS. Okay. So this is ohmic or linear region. This is cutoff or the device doesn't conduct, and this is saturation region. This is saturation region. It's a voltage control current source. So when the device is okay, so when do you tell that the device is in which region, right? So let me take the ring for that, right? So cutoff is simple. When VGS less than V threshold, the device is in cutoff, correct? Now when the VGS is more than V threshold, VGS is more than V threshold, there are two cases. One is it can be ohmic or one is it can be saturation, correct? So how do you tell whether the device is in ohmic region or saturation region? Anyone?
Based
Depends on VDS,
total
right?
voltage.
Correct. So you see what is the VD? Array, what happened, man? So you have VGS more than V threshold. Fine. You see what is your VDS. So you see whether VDS is more than or less than VGS minus V threshold. So if your VDS is less than V threshold, and over here if your VDS is much less than VGS minus V threshold, you tell the device is in ohmic region, correct? And if your VDS is more than VGS minus V threshold, then the device is in saturation region, and only then it will act as a voltage controlled current source, or else it will simply function as a resistor, right? Resistor is a passive element wherein the current through the resistor is not dictated by the device. The current through the resistor is dictated by the circuit operating conditions. You operate as a buck converter, depending on the load, the current is going to vary, and hence the device current will vary. Okay. If it is operating as a voltage control current source, only then you tell that I channel current or IDS for practical purposes is GM into VGS minus V threshold. Okay. So your IDS is dependent on VGS only if your VDS is greater than VGS minus V threshold. Okay. So your VGS, as your VGS increases, you are correct. As VGS increases, your ID will also increase. But when, under what scenario? Only when your VDS is greater than VGS minus V threshold. Now coming back to the output characteristic, you want to operate power electronic converter. I mean, in all the power electronic converters, you operate the device as a switch. Either it's properly turned off in the cutoff region, or it is properly turned on. That is, it is in the ohmic region. In the ohmic region, the RDS is of the order of few milliohms. Okay. So, and there will be some current flowing, let's say some 30 or even 60 amperes or how much ever ampere it is. The multiplication of both of that is V into I or I square RDS, whatever you do, it will be of the order of just a few volts. Okay, few millivolts to few volts. Okay, which means you will be lying somewhere over here. Okay, you may never even breach this saturation. So this is the saturation, right? This is the saturation region, and this is the ohmic region, correct? So you will be lying somewhere over here. You are operating as a switch. When you are operating as a switch, the RDS is going to vary based on your VGS only. The current will not vary based on VGS. Okay, but you are right in the sense that when we turn on the device, right, when you actually just turn on the device, what would happen? When you turn on the device, or when you give the what is happening? When you give the gate pulses, then what's going to happen is your VGS would increase something like this. Let's say, right? So this is 0, and I have what's happening? Right. So this is your VGS. So this is your V threshold, and this is 0, and let's say this is 18 volts. So from here to probably somewhere over here, let's say, okay, from here to here, see, from 0 to V threshold, the device is in cutoff region, okay, and from V threshold to some point, the device will be in saturation region. It behaves as a voltage controlled current source, but you will give a gate source voltage which is much higher. Okay, you will give a gate source voltage and make sure that the device goes into the ohmic region. So once the device goes into the ohmic region, the device current is no longer dependent on this GM into VGS minus VTH. Okay, the device current is dictated by the circuit conditions. So does this answer your question?
Yes, understood. Okay.
Okay, so you understand that when the device turns on, you are actually not directly going from cutoff to ohmic region. You are right in the sense that we will go from cutoff region. Then obviously we have to go through the saturation region. Without saturation region, we cannot reach the ohmic region. You are right in this sense. So during this saturation region, we will be modeling this, how the current increases and all later on, right? But during the saturation region, during that particular time, the device current is dictated by this condition. Okay. So for instance, again, I will go back to that same, yeah. So we drew something like this, right? That is IDS is increasing like this. So how it increases? This profile of increase is actually dictated by GM into VGS minus VTH. Okay. But point is, during this process, your gate source voltage is also actually increasing, and so you will transition from saturation region to ohmic region. Okay, does this answer your question? Or am I logged out? Yeah, so does this answer the question? Just we
Yes, it's
went
clear.
through the
Yes.
characteristics. Okay.
Yeah.
Okay. So yeah, I think it is much beyond time, and thank you everyone for hanging around. Yeah, but it was a very good session that you guys also interacted well, and it was also a good session for me. So anyway, we will meet up again next week on Tuesday from 6 o'clock. So yeah, good night everyone, and have a great week ahead. And by the way, the PPTs will be uploaded in the, I guess in the Google Drive. I think the link is also provided, so you can go over there and the PPT will also get uploaded. If you want to have a relook at the questions, right? Okay, so thank you everyone, and yeah, good night.
Thank you, sir.
Yeah.
Thank you, sir.
Bye-bye.
Thank you. Thank you, sir.
Thank you, sir.
Yeah, bye bye.